Good morning to one and all. So at the outset, I would like to thank the organizers of the ACM Summer School on Cyber Security at SSN. As Madam was mentioning, our interaction started with because of this summer school, and there is nothing like generosity. It's all our academic interest. See, we have already organized this similar summer schools and also winter school earlier. Then subsequently, when the request came, it's quite natural that there should be an opportunity to everybody. Okay. So, and also that SSN has its own reputation in the academic fraternity. Okay. So, if perhaps if it any another institute, perhaps we would also have thought about a second thought. But when it is from SSN, obviously there is no second thought. Okay. So, in that regard, thank you very much, madam, for inviting me to be the speaker of this particular talk. And ACM has started this concept of summer schools and winter schools way back in 2018 onwards, and subsequently these schools are getting organized. And I wish to appreciate all the participants who have taken their effort, right? And especially SSN has taken the initiative that to host the summer school exclusively for the women. So that's also a very good initiative. So in that regard, I would like to congratulate the SSN team for organizing this. So coming back to the today topic about security in the quantum computing era. Okay, so my talk would be focusing on the various topics related to security in the quantum computing domain. Before I go to the topic, I wish to mention that Madam was mentioning about your curiosity to learn emerging areas so that you can do the research. See, when it comes to exploring the domain, there are two things. One, pick up what is the niche people currently talking about and then do something there. And also there is a scope for the current topics that are already happening in security. So if you look at the security per se, there are fundamental problems that need to be addressed. It's not that only the quantum computing topic is the one that you should take and then proceed, but in security itself, there are so many problems. Say whether it comes to the encryption or whether it comes to authentication, there are fundamental so many problems that should be addressed. And above all that should be made user friendly, right? So there are so many topics. So you can choose and then proceed further, right? So, but now coming to the current topic, the quantum computing, we all know that, the people are talking about quantum computing, industry is investing hugely on that particular domain, and people are expecting that in the next decade, okay, by end of this decade or by next decade, we will have a quantum computers in practice, right? Now, when it is the scenario, obviously there are potential benefits of this particular domain of quantum computing, as well as there are certain threats. Both are there. Now, coming to the professionals from computing, we need to understand what are the benefits and how we can leverage quantum computing to solve the problems. That is one aspect. The second aspect is when it comes to the threat, what is the threat that quantum computing poses to the current technology? Are there any threats? If there are threats, how do we address them? So these are the two things that we should think about quantum computing. Now, in these two dimensions, when it comes to the security, there are two things that people talk about. Number one, people talk about post-quantum cryptography. The second one is quantum cryptography. These are the two terms people talk about. Okay, there is a difference between both. When it comes to post-quantum cryptography, when it comes to quantum cryptography, there is a difference. What I said few minutes back, I said when it comes to quantum computing, we need to understand how we can derive benefit out of the quantum computing. So quantum cryptography is all about how we can leverage quantum computing principles so that we build secured systems. That is about quantum cryptography. So the second dimension is the quantum cryptography is about I have quantum computer. How do I leverage this quantum computer so that I can derive better security. So that is about quantum cryptography. Then what is post-quantum cryptography? Post-quantum cryptography is all about, yes, there is going to be a quantum computer. Are there any threats from quantum computer? Okay. If there are any threats, how we are going to address them? Do we need to develop new techniques so that my current systems are secure from quantum computer? That is about post-quantum cryptography. So one should understand, okay, now I want to work in quantum computing and security, where I should work. Should I work at quantum cryptography? That means I am going to leverage quantum computing principles and build new techniques, protocols, algorithms such that my quantum computing would be used for securing or enhancing the security. So that is about quantum cryptography. No, I wanted to focus on post-quantum cryptography. What is post-quantum cryptography? As I said, you have a quantum computer, it is going to pose challenge, it is going to pose threat to the current cryptography or current security standards. How I am going to protect it? That is about post-quantum cryptography. So once if we know the fundamental difference of these two things, then we can proceed further. Now, but underlying both of these two things, what is the underlying principle? Number one is the cryptography, right? So cryptography is the bottom line. You might have past few days, you have heard about security, and in that probably you listened about the cryptography, then network security. When it comes to network security, you must have discussed about, look at the TCP/IP protocol stack, how you are implementing the security per se. So take an example, you are having gadgets at your lab using, say connecting to the internet. How my communication is secure through my internet? Obviously, bottom line is your cryptography, right? So take an example, your application layer security or your network layer security, anywhere, okay? Anywhere, transport layer security, everywhere you have cryptography in place in such a way that your communications are secure, your transactions are secure. Now, when client is contacting the server, there is a handshake. With the handshake, what you do? You establish security primitives. Like before commencement of this session, what madam did? She introduced. Why she did it? It's kind of a handshake. What happened in that handshake? She introduced about me. Similarly, when a handshake happens between the client and server, they exchange certain cryptographic primitives. In the sense, what are the cryptography that client can understand? What are the cryptographic algorithms server can understand? Once this handshake is done, then finally at the end of the handshake, you have a key that gets established between client and server. Once you have the key, what you can do? Once you have the key, what you can do? Okay, so take an example, I'm a client and you are the server. So what can be done? We have handshake completed. So once handshake is complete, you have the key gets established. Once you have the key, that means when I say key, it is the symmetric key. All of you have understood symmetric key. What is a symmetric key encryption? Both the communicating parties will have the common key. So when once we understood the common key, that is known only to both of us, no one else knows that. So we can obviously encrypt and decrypt using that particular key. So, but for that purpose, you need to have a handshake. Once handshake is done, key gets established. Once key is established, secure communication takes place with the help of symmetry. Okay. So obviously, when it comes to network security, bottom line is cryptography. All of you have seen HTTPS. What is HTTPS? HTTP over secure hypertext transfer protocol with security. Okay. So how it is done? It is done with the help of your transport layer security TLS. So bottom line is cryptography, right? So once if you understand that the bottom line is cryptography, and coming to the quantum computing, Number one, cryptography can leverage quantum computing and provide more security, or else cryptography, the current cryptography standards have certain threats. Now, my talk would be covering these concepts. Number one, I will be touching about some of the cryptographic algorithms. Then I will be talking about quantum computing principles. Then I'll be discussing about algorithms such as Shor algorithm, especially, which is posing the threat from quantum computer perspective towards public key encryption algorithms such as RSA. Okay, all of you have heard the word RSA. RSA is a public key encryption technique. Similarly, there is another algorithm called Diffie-Hellman algorithm, which is a public key encryption technique. So all these public key encryption algorithms are having severe threat from quantum computer algorithms such as Shor algorithm. And obviously there is a question, sir, is it that only public key encryption algorithms are having threat? No, even the symmetric encryption algorithms are also having threat. From which algorithm? There is an algorithm called Grover algorithm, which is posing threat for symmetric encryption algorithms. Tell me one example for symmetric encryption algorithm. Yes, DES and AES, right? So DES, AES, these are all symmetric encryption algorithms, right? So these encryption algorithms are having threat from Grover, but there is a mitigation way to mitigate this particular threat from Grover by increasing the key space for symmetric encryption algorithms. But that is not the case for asymmetric encryption algorithms. Right? Then also I will be talking about post-quantum cryptography. Then I will be talking about quantum key distribution. Quantum key distribution comes under quantum crypto, wherein which we are leveraging quantum computing principles for key distribution problem. Right? So this would be the overall presentation. Right. So you must have already understood confidentiality, integrity, authentication. Already you have discussed perhaps either in your academic programs or in the summer school. You must have learned about security fundamentals about confidentiality, integrity, authentication, availability, non-repudiation. These are all when I say security, I infer or I understand that these objectives are met. Okay. It's not that security is a single word. Security has these objectives to be met about confidentiality, integrity, authentication, availability, non-repudiation. These are all various fundamental objectives to be achieved in the security. But how do I achieve? There are means with which we can achieve it. Similarly, if you look at the algorithms, when you look at the algorithms, there are algorithms that utilize the traditional CPU, okay, conventional computers CPU clock cycle, CPU speeds are increasing, right? Year after year, CPU speeds are getting increased. If you look at the way we are increasing the CPU speeds, if you look at, either by increasing the clock cycles, you can increase the speed of the things and number of instructions executed by the CPU. But this is one way you can enhance the speed of the system. But on the other side, of course, you have parallel computers, you have distributed computers. What happened in 1994? Peter Shor has formulated an algorithm called Shor algorithm under the assumption that if there is a quantum computer, even now today we don't have a practically potential or a commercial scale quantum computer even now, but in 1994 itself he formulated an algorithm for quantum computers that would have the power to identify secret cryptographic keys in an efficient manner, right? So in 1994 when he brought this algorithm, people do not know how to build the quantum computer. Okay, but now at least now there are algorithms, there are quantum computers, with few qubits from IBM, Google, and etc. So there is a chronological order of history of the way the quantum computers are have come from 1920s, you have the theoretical concepts, then physics aspects of the quantum computers have started, and at present now there are certain companies which have announced that yes, they are able to achieve quantum supremacy with certain hundreds of qubits, say about 50 to 100 qubits speed. So as I said, this particular talk would be talking about cryptographic techniques which include symmetric, asymmetric and digital signatures, and I'll also be talking about quantum computing principles, then quantum cryptographic techniques. Now look at the general scenario which everyone be aware of it. There is a sender called Alice. Similarly, there is a receiver Bob, and you have an untrustworthy network, that is a public communication channel, and who is listening to that particular communication channel is the Eve. What are the problems when you have such unsecured public communication channel and the communicating parties are using that communication channel is, number one is that the channels are spying on the data, channels are modifying the data, which these are all the problems related to confidentiality, integrity, right? So also authentication is another problem. Now Bob wants to know that when he receives a message, who has sent this message? Who has sent this message? Is it that the message has come from Alice or not? So it is user authentication. Number one. Number two, the message that what I received is the actual message sent by Alice or not. This is the message authentication, right? So in authentication itself, you have user authentication, you have message authentication. Understanding that the message is sent by Alice or not, the user. This is the message that was sent by Alice, is message authentication, right? These are all the various problems you need to address when you are having a scenario of communicating parties using a open communication channel which is untrustworthy. This is one particular aspect of it. Another aspect of it is, we are always thinking Alice is sending a message to Bob. Bob is also responding back, under the assumption that the communication channel is untrustworthy. I'll give you another problem. The problem is, what if Alice and Bob both themselves don't trust each other? Okay, what if? Now the point is here, communication channel is untrustworthy. It's an open channel. These are all the problems that what we narrated is about, focusing on the communication channel. Number one, integrity. Number two, confidentiality. Number three, authentication. Under the assumption that communication channel is untrustworthy, but Alice and Bob both trust each other. Is it that always happens like that? Obviously not. Alice may trust Bob, Alice may not trust Bob also. Similarly, Bob may not trust Alice. When you are having a communicating parties, like when people are making the transactions, I don't trust. Why imagine that you are buying something from me? Why you should trust? There is no role of trust here. So imagine if there is no trust between the communicating parties, how do I see that particular security problem? It's a security problem. How do I see that security problem and how do I handle it? It is through digital signatures. Okay. So you need to understand what is the solution I am going to bring in. Okay. So if you look at the cryptography, there is a vast history for the cryptography. It is not that this cryptography, which is nothing but art and science of writing secret codes, is not started just now. It started way back, right? And what we are focusing is this modern cryptography, which is the cryptography related to the digital computers, right? So you have two types of systems: symmetric crypto systems and asymmetric crypto systems. Symmetric crypto system, which you have already mentioned, wherein which both the communicating parties have agreed a common key and they are communicating with each other. In asymmetric crypto systems, there is no common key. Every communicating parties will have what they will have? Alice and Bob will have, that is symmetric, right? What is asymmetric cryptography? Correct, correct. Now Alice and Bob will have, correct. So every communicating node or a person, user will have their own key pair. Their own key pair. That means now how many of us are here? Say take an example around 20. Every person will have key pair. You have your own key pair, I have my own key pair, right? So think like this. Imagine all of us wanted to communicate using symmetric encryption technique. We have 20. Then how many keys are required? Think and tell. Is it one is enough? No. For you and me, one is enough. You need how many keys? You need 20 keys, right? You need 20 keys because you can't use the key what you are using with me, with her, with madam. Similarly, madam has to maintain 20 more keys because she has to use one unique key with everyone. So one key with me, one key with the other participant, one key with the other participant, like this. It's a huge problem. Now you need to understand why people went for asymmetric cryptography, right? Why people went for asymmetric cryptography is initially we have symmetric crypto systems. Then people realized that key management is a huge problem. How many keys I have to manage? No, now we are talking about 20. Imagine I have about thousands. Can I manage 1000 keys? How do I manage? So that means when I am talking with the 1000th person, I have to check what is the key I have established with him, and then accordingly I should use, which is practically impossible. So people went for, okay, what if I don't have to maintain these many keys? Instead, I will keep my key pair. When I keep my key pair, what happens is I have, so I take an example, node 1, node 2, node 3. Then what happens? Every node will have their key pair, public key 1, public private key 1. Similarly, node 2, public key 2, private key 2. This is for node 3, public key 3, private key 3. Right? This is how it goes. Is that covered? You might, is that, I hope you are aware of this. Otherwise, we have the slides. I'll be talking about that. There is no problem. So what happens now? I have 3 nodes in this scenario. Every node is maintaining how many keys? Actually, it is 1. That means a key pair. Otherwise, every node has to maintain 2 more keys. If it is a symmetric technique, that's the problem. So key management is a huge task. So people went for asymmetric cryptography. Now, when it comes to asymmetric cryptography, every node will have a key pair. One key they can keep themselves with as a public key, private key. Another key they can open it as a, another key they will open it as. So I keep my private key and I open my public key. So that's how I am using one key for encryption purpose, another key for decryption purpose. So that's why you call it as asymmetric, because you are using one key for encryption, another key for decryption, right? So now coming to these techniques, we said symmetric and asymmetric. When you look at the algorithms, you have, somebody said DES, AES in case of symmetric, and there are so many other algorithms, right? When it comes to cryptography with symmetric keys. When it comes to cryptography with asymmetric keys, that means public keys, you have so many algorithms, which includes popular one among them are RSA, Diffie-Hellman. These are all digital signature algorithm. These are all popular cryptographic algorithms which comes under asymmetric keys. Is that clear? Now, remember, we are trying to address what is the problem? Problem is we are using a untrustworthy communication channel, and we wanted to provide what services? Confidentiality, integrity, then availability, then authentication. So these are all the objectives that we wanted to meet, right? Now, what happened is, now imagine your untrustworthy network is having Eve is having a quantum computer. Then what comes to the problem is all the cryptographic algorithms that are with public key encryption comes under threat. Okay. So all this cryptographic with public keys comes under the threat, right? So now the question is, when they are in threat, so what happens? What will happen if they are in threat? What will happen to us? But if we want to know that, we need to understand first of all how public keys are used. Okay, so if you look at how, first of all, how public keys are created, what I said, I have my key pair, you have your key pair, she has her key pair. What is that pair contains? One with, so imagine Alice, public key of Alice, private key of Alice. This form key pair. First of all, how do I generate that key pair? How do I generate such key pair? So for that purpose, Alice generates a, first of all, a large random number to generate her public and private key pairs. And from that random number, what she is going to do is apply prime factorization algorithm, from which she is going to get her PUA, that is public key, PRA, that is private key of Alice. If you observe in asymmetric key encryption algorithms such as RSA, this key generation itself is a complex task. Okay. So once the keys are generated, what these keys are going to be used, right? How these keys are going to be used. If you look at Alice, public key would be used because, can I use Alice public key or not? Imagine I have my public key, private key pair. Can you guys use my private key? Why? Because it is private. Can you use my public key? You can use my public key. So what Bob is going to do is use Alice public key and encrypt the message. So Bob message is hello Alice, encrypt it using the Alice public key, because Bob knows Alice public key, and encrypt the message. This is your ciphertext, right? And what Alice is going to do? Alice has to decrypt. How Alice would use the decryption? Which key Alice would use? Which key Alice would use? Private key of Alice. Alice knows her private key or not? Obviously. So Alice would use her private key and decrypt the message. Now if you look at this scenario, encryption has happened with which key? Of not both. Whose public key is used? No. Bob has used whose public key? Alice. Alice is the receiver. So receiver's public key is used for encryption purpose, right? And that's the reason why we are calling this as public key encryption scheme. Similarly, Alice is using her private key. So that means she is using her private key, and then the encryption is decryption is done. Can I use? Sir, you may get a doubt. Sir, this is what is happening with symmetric keys also, right? Symmetric key, we establish the symmetric key and then we can encrypt and decrypt. But why we went for public key schemes? Why we went for public key schemes? Few minutes back I mentioned. Sorry? Okay. Okay. What is the other answer? Okay. What is the other answer? Key management, right? Because if I go for symmetric key, I can't manage the keys. I have to manage, if I have n number of nodes, I have to manage n minus 1 number of keys. It's impossible, right? So that's why I went for public key. Now, one point you mentioned about fastness, in fact, not public key schemes are faster, symmetric key schemes are faster. Okay? The reason is, the reason why symmetric keys, the reason why public key schemes are not faster is, you have a complex task of this one. What is the task? Creation of public keys. That is the huge task. That's not possible. That is a complex task. That's the reason why you are going for the, you prefer symmetric keys. But symmetric keys challenge is key management. So what people do is, people establish symmetric keys with the help of asymmetric keys. This point was discussed. Okay. So what is that? Why we are using asymmetric key schemes? Asymmetric key schemes are used for the purpose of establishing symmetric keys. What is this problem? What is this problem? Establishing secret key. So it is like this. Alice and Bob, they wanted to communicate with the help of symmetric key schemes. What they need? They want to communicate with the help of symmetric key schemes. What they need? What they need? Secret key. Now, how to get that secret key? How to get that secret key? I said one problem. What is that? Maintaining multiple keys with multiple people. That is one problem. Another problem is, okay, there are no multiple people, only two people are there. But how this key goes between these two? That is another problem, right? That is another problem. How a common key gets established between both Alice and Bob. Symmetric key is a common key, right? So imagine I have a common key called K. Okay, common key called K. Alice has created this common key. Now how it goes to Bob? How it goes to Bob? Okay, it is like this. There is a bag there, right? For that bag, imagine there is a lock. And this locked bag is dispatched to your native place. And your parents have received that bag. How they open that bag? They need that same key, right? Who is having that key? You are having the key. But how they open it? Now, yeah? No, see, that's what is the problem. Alice has created the key right here. What you are talking is, sir, there is a duplicate key. They are also having it. But the scenario what we are talking here is that Alice has created the key, encrypted the message, sent that message. Now who is having the key? Alice is having the key. But what about the Bob? No. So what you do in this scenario, courier, so you sent this bag by courier. Will you give that key also to that courier? Array, here you take this bag, this key also and give it to my parents? Will you do that? Why? Why you don't do that? It will be, yeah, correct. It is unsecure. Even the courier fellow can open it. That is the what is communication channel is unsecure. It's an untrustworthy channel. So you don't believe that guy. So what you do in that case? Okay, I am sending this bag via DTDC. I send this key via another courier called first flight, speed post, something, right? So I am using what? A different communication channel. So your bag is going in a different communication channel and your this thing is going in a different communication channel. Now do you understand when you are making online transaction via your browsers and mobiles, where you are getting your OTP? SMS, right? SMS is coming OTP, right? So you have a different communication channel to get it. Now the point is that now again let us come back to this question. What is the question? Alice is created the key, encrypted the message and sent it to Bob. Alice has created the key, sent the message to Bob by encrypting the message and creating the ciphertext. So C is equal to E of M comma K. Now question is how K goes to Bob. That's the question. There are so many schemes. What people realized is that the best way is I use asymmetric key technology. When I have asymmetric keys, Alice will have public key, private key, right? Bob also will have public key, private key, right? Bob also will have the keys. Now, what Alice knows? What Alice knows? Bob's public key. So, what Alice would do is encrypt the key with the help of public key of Bob and send it to Bob. Now Bob can decrypt this. Bob can decrypt this or not? How? With the private key of. So decryption happens with the help of, imagine I am calling this as some K1. Decryption happens with the help of private key of Bob to get back. Now Bob is having now communication happens with the help of secret key. Using which algorithms? Symmetric key encryption algorithms. Because now you have the key. Okay. So you need to understand one thing is that your asymmetric key technology is used for the purpose of establishing the symmetric key. Once you establish the symmetric key, communication happens with the help of symmetric key encryption. So now the point is, if quantum computer comes, what is going to get hit? What is going to get hit is this. If this gets hit, what will happen? You can't establish the key. You can't establish the key, your symmetric key gets affected. This is the point. Are you able to follow? Now the question is, sir, why to use symmetric encryption and think about establishing the common key and further go for asymmetric? Instead, I will go directly for asymmetric key encryption. Right? Why to go for symmetric, then to do key establishment, go for asymmetric, I go directly for asymmetric. The reason is, she said, faster. What I said, asymmetric is not faster. Asymmetric is okay for key establishment. Tell me, when I have a message and a key, which one would be larger, message or key? Obviously, messages are huge in size. Keys are fixed in size. So, I can encrypt freely my key with the help of asymmetric. If I try to encrypt plain text with asymmetric, we are out. We don't do that. Okay. Small messages like hello, hi, these things, that's okay. That's no. We are talking about large plain text messages. We don't encrypt with asymmetric systems. We encrypt with symmetric. So when you encrypt with symmetric, the question is key establishment. Obviously, we go for asymmetric. Okay. So now the question is how public key schemes are used to create symmetric key is this. Whatever this diagram that is shown here is that. Okay. Once you have symmetric key, the second diagram what is drawn here is about this. Once you have the key is established, what will happen? Both Alice and Bob would interact with symmetric key encryption technique. So now you understood, you have the symmetric key technology, you have asymmetric, that you guys must have already understood. But the point is that what is to be used when is this, okay? What purpose? Now, all this is about when Alice and Bob are interacting and they know each other and they trust each other. Again, you are sending this bag to where your native place, your parents. They receive this bag and you trust it. Imagine you are sending this bag to someone whom you do not know. He will receive the message and say that no, I have not received. It's an untrustworthy communicating note. So what you do for that? People attach one acknowledgement slip to that. So the moment they receive, they have to sign on the acknowledgement slip and you receive it back, right? So in a similar manner, when your communicating parties are trustworthy and all that, whatever we have discussed. Now the question is that now, imagine these two communicating nodes, Alice and Bob are interacting and there is a fellow called Eve who is listening to the communication channel, who has the ability to modify and all that. That is one issue. Another issue is that both Alice and Bob don't trust each other. In such scenarios, what you need is not confidentiality, you need signatures, right? Whenever you see a circular, you see a signature, right? Somebody signs, the HOD, faculty, you need to sign. Why you are signing on the document? We sign on the documents, right? Why do we sign on the document? It's a physical signature on a physical document. Now we are talking about digital signatures, public key signatures. So now if you look at the signatures, Alice is sending a document. So Alice has a private key and a public key. Key pair is there. Now, everyone knows what is this? What is this? Of Alice. So everyone knows this. This is the public key of Alice. What Alice is doing, Alice is signing the message with, this is private key, right? Signature happens with the private key of signer. Who is signing the document? Alice. Alice is sending a message to Bob. She will encrypt that message with the help of, few slides back we discussed. When Alice is sending a message to Bob, Alice wanted confidentiality. Alice will encrypt that message with the help of public key of, that means receiver's public key is used for confidentiality purpose. Now what we are doing? we are signing. Sender is signing the document. So for signature purpose, which key is used? Which key is used for signature purpose? Private key of sender. Yes, sender. So receiver's public key is used for encryption purpose to achieve confidentiality. Sender's private key used for signing the document. Once you sign the document, document has to be verified. Who signed this document? How do you verify? Imagine I signed the document and it is circulated. You know my signature and you see that, okay, yes, this is signed by so and so. Now come to the digital signature. The signature is created with the help of private key of the signer. How it gets verified? It gets verified with, in that pair, what is that is known? Public key of signer, right? So you guys need to understand digital signatures are created with the help of sender's private key. Digital signatures are verified with the help of signer's public key. Now, in either of these case, the point is that which encryption algorithms we are using? Asymmetric. Now, if quantum comes into picture, what is going to get hit? We already said your key establishment problem in the symmetric key schemes get hit. What is the other problem? Digital signatures. Digital signatures. So, when quantum computer comes into picture, what are the you are going to get affected is the digital signatures also. If you don't have digital signatures, you can't make online transactions, you can't do the digital transactions, right? So this is about when you want to deploy cryptography. This is the product life cycle goals, how this gets implemented. But remember, it is not a waterfall model. I'm going to skip this. This is about DES. I think you have undergone this data encryption standard algorithm, which is which encryption? It is a symmetric encryption, first commercial standard introduced in early 70s and was there till late 70s and was there till early 90s. Okay. So what you do is you take the plain text, divide the plain text into blocks. Blocks are of fixed size, which is 64-bit, and you take the 64-bit key and perform the encryption block by block. Okay. So this is about DES. Now the challenge with the DES is your key size. What is the size of key? Is 64-bit key. And the DES follows a structure called Feastel structure, wherein which there are about 16 rounds of operations, right? So accordingly, your key also gets iterated, and every round you give the round keys, and finally you get the ciphertext of this particular block. So imagine you have first block 1, you have to do this, and then imagine you have block 2, you have to do this activity. Like this goes. This is DES, data encryption standard. People realized 64-bit key is of no secure, so they went for double DES. What is that they did double DES? So they increased the key space. So 64-bit key 1, 64-bit key 2, another key. So that means again encrypt the ciphertext. So with that, K1 you perform encryption, then again take K2 perform encryption. 2 times when you encrypt, your key space gets increased. But what happened is that with that increase, there is an attack called meet in the middle attack. People realized that there is an attack called meet in the middle attack, which is not there with DES, that got introduced. Then they went for triple DES. Now still there are some of the applications where triple DES is being used, but more or less the DES got wiped out. Then you have AES. which currently being used, okay, in almost majority of the applications. AES is the current standard. Now, if you look at the flexibility of AES is that AES is going to provide, the key length of variable in nature, either 128 bit, 192 bit or 256 bit. So accordingly, AES would be called as AES 128, AES 192, AES 256. Remember, your block size is fixed. Plain text block size is always fixed, which is 128 bit. Okay, and your key length is getting varied. When you look at DES, what is that? Your key length is fixed, block length is fixed. When it comes to AES, your block length is fixed, your key length varies. You can choose. Okay, and accordingly, the number of iterations that happens in the cipher, that also varies. I'm not going to touch this AES, but the beauty of AES is that you have four operations that gets performed on AES. Is that discussed? AES has four operations, just four operations. What are the operations? Substitute operation, shifting of the rows, mixing of the columns, add round key. Okay. Among them, this is the beautiful step called mixing of the columns. Okay. This brings non-linearity to the AES algorithm, and hence your strength lies with mixing of columns. So these are the four operations. With these four operations, AES is proved to be secure, and even it can resist the quantum attacks. Which is AES is which encryption algorithm? Symmetric or asymmetric? Symmetric encryption algorithm, right? So I'm not going to touch the details of the algorithm because that itself takes time. If you observe, the most important thing is each stage is reversible. Remember, encryption should be reversible or not? Why it should be reversible? Correct, because it is to be decrypted. If I am not able to reverse it, can I decrypt it? No. So every step of your encryption process should be a reversible operation. Okay. So this is about the structure of AES, what happens in each round, performing the substitution operation. So every time, this is the initial state. When you perform a transformation, you get a new state. Then you perform a transformation, you get a new state. Then you perform a new transformation, you get a new state. Final. So you see here there are about 4 transformations: 1, 2, 3, and 4. Substitution of bytes, which is fixed. You say that in this particular byte, it should be substituted with this. It is fair enough, linear transformation. Similarly, shifting of rows says that, look at this row and shift by 1, shift by 2 to the left, to the right. So shifting of rows is also a linear transformation. Then the mixing of columns is a non-linear transformation, okay, which is the strength of AES. Then you have add round key, because you are performing number of rounds of this operation. From the given key, you generate for every round a new key, and that's get added. So you get a new round here. Okay, so you enter into the new round. 10 rounds if it is 128 bit AES. So this is how it goes. So this is about your encryption process, and this is your decryption process. Okay, reversible operations. Okay, and remember, those who are really interested, building these blocks, this itself is a research problem. Operations. How do I substitute? When I say that I am substituting one byte with another byte, which byte I should substitute? On what basis? So it is called S boxes. Designing the S box itself is a problem. Okay. In Coursera, there is an exclusive course only on designing the substitution boxes. Okay. So those who are really interested, as I said, This domain has lot of opportunities. Now this is about symmetric. Again, asymmetric, what so far I have covered is the one which I will be quickly going through it. So asymmetric technology is, we also call it as public key, and the beauty of this public key scheme is that, or the requirement is that, we said there is an Alice as key pair, PUA, PRA. PUA is public, PR is private. Few slides back, I said key generation is the complex task. Why it is complex? I am just generating two keys. I cannot just like that generate two keys. Number one, the requirement is that among that pair, I am keeping one as public. One I am keeping it as private. So in the pair, if I reveal one, attacker should not understand, infer, calculate private part. By knowing public key, attacker should not infer, calculate, deduce the private key. I should generate keys like that, pairs like that. That is my fundamental requirement of public key pair. So when I am generating key pair, it is not that randomly I take some number and say, announce that, look, this is my public key and the other is my private key. That is one fundamental requirement. The second requirement is that, look, when you say, yes, I have one key kept public, other key as a private, knowing one another key should not be calculated, that means there should not be any kind of a relation. Is it that there should not be any relation? If there is no relation, when public key is used for encryption purpose, decryption is happening with private key, right? So is it that there should not be any relation? There should be relation. You understand? There should be relation between key pair, in the sense public key and private key, there should be some relation, but that relation should not be revealing to the attacker. If it is revealed, then from public key, attacker will calculate the private key. Okay. So that's the reason why your key generation process should be carefully done, right? So again, when it comes to usage of these public keys, is it that I am using always public key for public keys only for encryption and private keys only for decryption? No, right? We have seen a scenario. What I have used? What I have used? Is it that always in the public key cryptography use techniques, is it that I am always using public key first and then private key later? There was one application where I have used private key first and public key later. What is that? Digital signature or authentication, right? So when I want confidentiality, what I do is, so confidentiality, I use public key of receiver for encryption, private key of receiver for decryption. This is confidentiality. What is the other application I said? Authentication, right? And signature. What I do? Private key of signer to sign, public key of signer to verify, right? So in the key pair, public key, private key pair, confidentiality is achieved with the help of public key of the receiver and decrypting with the help of private key of receiver. Authentication or signature is achieved with the help of authentication or signature. How it is done? First, signing with the help of private key of signer, and verification happens with the help of public key of the signer. See, I signed the document and you verify, right? It's not that I sign and I verify. When I sign with my private key. When you verify with my public key. So when you have this key pair, and the key pairs are created with the help of public key encryption technique, and for what purpose I am using? Now the question is, imagine my application requirement is confidentiality. If I encrypt with the help of private key of sender, what will happen? Tell me whether I am achieving confidentiality. I have encrypted the message with the help of private key of sender. Encryption with private key of sender. Decryption happens with when it is encrypted with the private key of sender, decryption happens with not private key. The encryption is happened with private key of sender. I am sending you a message, madam. I have encrypted with my private key, and you decrypt with my public key. Is it that you alone can decrypt this message? She also can decrypt, right? Why she will be able to decrypt? Because decryption is happening with my public key. My public key is known to you only. It is known to everybody. So what is lost when you encrypt the message with the sender's private key? Confidentiality is lost. Okay? Confidentiality is lost when you encrypt the message with sender's private key, right? So that's the reason why which key you are using for what purpose is important. Now the question is, sir, is it that I achieve both my confidentiality and authentication? Of course, you can achieve both confidentiality and authentication. Look at this diagram. Okay, look at this diagram. Alice is sending the message to Bob. Okay, so message X is first encrypted with private key of Alice. The message is encrypted with the help of private key of Alice. When you encrypt the message with the private key of the sender, what is that you achieve? Typically, you achieve authentication or signature. So, by doing this, you are trying to get authentication or signature. So, what you get is an intermediate text. This text is again encrypted with the help of public key of. When you encrypt something with the help of public key of receiver, what is that you achieve? Right? Now you send this ciphertext to receiver. So the receiver, Bob, first has to decrypt this. So for that purpose, what is that the receiver is using? Private key of Private key of Bob. Bob has private key. So this encryption is getting decrypted here. You get why? Now if you closely observe this Z, can anybody break that Z? Because Z is created with the help of public key of Bob. To decrypt that Z, what is needed is private key of Bob. So in the communication channel, open channel, what you have is Z, which is created with the help of public key of Bob, right? So to decrypt it, you need a private key of Bob, which only Bob has. So once Bob decrypts it, Bob gets Y, which is created with the help of private key of Alice. To decrypt it, what Bob need? Public key of so decrypt it, get the message. So what is achieved now? Both confidentiality and authentication. So now this X message would not be the plain message, it would be the key if you are exchanging the key. Okay. So this is how your public key crypto systems are getting implemented. Which one, madam? No. They don't exchange, they calculate. Okay, Alice would calculate her key pair called PUA, PRA. Similarly, Bob has to calculate by himself public key of B, private key of B. He has to calculate, they don't share. What is getting exchanged here is that now Alice needs to know what is Bob's which key Alice need to know? Public key. Similarly, Alice need to know Bob's public key. Anyway, it is a public key. Of course, though I am saying anyway it is a public key, you can't just like that assume that public key would be known everybody. Imagine there is a security threat there. What is that threat? Imagine my public key, I am announcing it. She is modifying my public key and saying that her public key as my public key. What is lost? Not confidentiality, authentication. Authentication is lost. So that's the reason why we are trying to achieve I didn't get you. Yeah, Alice has to calculate key pair. No. It is okay. You are assuming that both PUA, PRA, similarly PUB, PRB are same. No, they are totally different. You have your key pair. I keep my key pair. I don't know your PU. I don't know your PR, your private key, and you don't know my private key. Yeah. I will show you the RSA algorithm, madam. You will be able to understand. Now, so to clarify, madam, this thing we have RSA algorithm. RSA is discussed. RSA is discussed here. RSA. Yeah. Yes. So generally it is discussed. Look at the RSA algorithm. RSA is popular, widely applied public key encryption algorithm. It is was proposed by Rivest, Shamir and Edelman in 1977. It is a block-based cipher. Okay. The strength of this particular algorithm is with a particular phenomenon called there is a challenge in finding prime factors of a large number. That's the challenge which so far people could not identify, but quantum computers are going to break it. That is the strength of RSA, which we will discuss later. Now, as madam has asked, how do I generate? Now, look at Alice. Okay, what Alice is going to do? First, Alice is going to create her key pair, PUA, PRA. Same process, the same algorithmic steps, even Bob has to do, anyone has to do. Now, what is the first step? Generate two large distinct prime numbers PQ. Steps are important. The reason is that this is getting broken by quantum. So, what is the first step? Generate two large random distinct prime numbers. Now, this is the first step. Now, observe the first step. First of all, you have to generate a number. How do you generate a number? Okay. What number? Random number. Now, imagine I ask you a question. Tell me a random number. Tell me one random. Randomly, you tell one number. 13, 12. What is the, why you said 13? It's a random number. Now, how the system generates this number? It can't generate it on its own because you said 13 or you said 12 out of your instinct, right? Is the instinct for that? So it needs some algorithm to generate that number. It can't generate on its own. So whatever the numbers that the computer generates, you don't call them as random numbers, they are pseudo-random numbers. They take the current clock time, from that they compute, do some activity and get a random number. Now, what is the second challenge? That number should be prime. How many such numbers should be generated? 2. So that means you should first generate a number and then test whether that number is prime or not. And similarly, you should generate a second number. Once you do that, and another thing, both numbers should be of same size. Once you do that, you calculate their product. That is the second step. N is equal to P into Q, right? Then, after that, create a third step which is called Euler's totient value called psi of n. What is n? P into Q. Euler's totient value over n would be P minus 1 into Q minus 1. The rationality for it is the number of positive integers. What is meant by Euler's totient value is the number of positive integers which are less than n and relatively prime to n. That means what actually you are doing is starting from 1, 1, 2, 3, 4, like that you keep checking till n, that number n and that one GCD of it. Then you see whether they are relatively prime or not. Or simply you say that it is nothing but P minus 1 into Q minus 1. Okay. Then after that, the next step is select a random integer e. Okay. You are choosing a random integer e. What is the condition? That e should be less than psi of n, which you have calculated here, and e again should be relatively prime to psi of n. That means that is the condition. You have to generate a number called e, where e is less than psi of n and it is relatively prime to psi of n. That means GCD of e comma psi of n is 1. Then this is another step called you are computing an unique integer d. How you are computing that d? D is multiplicative inverse of e. That means when you multiply e and d, which is congruent to 1 at mod psi of n. That is the condition in which you should create or calculate a d. So condition is d is less than psi of n and d is relatively prime to psi of n. So these are the 5 steps in RSA algorithm. Okay. So you took 2 large prime numbers, you calculated their product. Once you did that, you have calculated the Euler's totient value of that product value, which is psi of n. Then you have chosen a random integer e such that e is less than psi of n and e is relatively prime to psi of n. So you have chosen e. Once you have chosen e, what you did? You calculated a d. What is the relation between e and d? E and d are multiplicative inverse. Okay. What is meant by multiplicative inverse? When you multiply them, you get an identity number which is 1. So e multiplied d is congruent to 1 at where? At mod psi of n. This is the 5 steps that you have. These 5 steps Alice has to do. Similarly, Bob has to do. Everyone, whoever wanted to generate their key pair. So now the question is, what is the key pair? The key pair is public key is n comma e, private key is these steps I am generating, these steps you are generating, like that everyone are doing these steps. Once you complete it, I am keeping my e comma n as public and I am keeping d as private. Similarly, you will do that. Similarly, X will do, Y will do, Z will do, everybody will do. So they have their own key pair. Now, what is open? E comma n. What is private? D is private. Now, by knowing E and n, can attacker calculate D? In order to calculate D, first of all, E and D are having a relation or not? E value and D value are having a relation or not? Yes, they have a relation. What is the relation? I said they are multiplicative inverse. When you multiply E and D, you are getting 1 at mod psi of n. ED is congruent to 1 at mod psi of n. Now, having known E value, in order to calculate D value, what is needed? What is needed? Is it n or psi of n? What is psi of n? P minus and P minus 1 into Q minus 1. That means what is that you need? P value and Q value. That means prime factors of n. Prime factors of n. So having known En values, to calculate D value, what is needed? Prime factors of n. If you know prime factors of n, attacker will be able to calculate D. Now, what is the encryption happening? Encryption is simple step. Yeah. So I'll stop with this encryption decryption, then you can go from there. So encryption happens. How with the encryption happens? You know, En is the public key, D is the private key. How encryption happens? In asymmetric key schemes, with the help of which key? Public key, right? So that's why you see here, M is my plain text, ciphertext is C is equal to M power E mod n, where your En are public key, right? E comma n are public key. So encryption happened with, decryption happens with. So what is that variable? D. So see that decryption is, take the ciphertext C power D mod n, you get the plain text M. You understand? When I am sending the message, which En I will use? Imagine I am sending it to you, madam. Which En I will use? Your En I will use. Which D value you will use? Your D value you will use. Right? This is simple. Encryption and decryption is simple. Now the question is, as I said, if you look at the ingredients of the algorithm, P, Q are prime numbers. Remember, they are chosen. Okay, and they are kept private. N is equal to P and to Q, which you calculated it, and N value is private or public? N value is public. Now, E value is chosen value, and is it public or private? Public. Now, D value is calculated one, wherein which D is multiplicative inverse of E at mod psi of n, and it is kept private. In order to calculate D, what you need is psi of n. In order to have psi of n, you need to know PQ. Okay. Now the point is that your RSA is still whole, secure. The reason is that, remember, we are not talking with simple numbers of 2 digit, 1 digit. We are talking about these numbers of length, some 100 digits, 200 digits, 300 digits. Say, take an example, as of known, the largest known prime number has somewhere around 2 crore 48 lakh digits, the known prime number. Okay, so we are not even talking about such magnitude, but we are talking about some 200 digit number, 300 digit number. Okay, when you take it, finding the prime factors of that, if you want to crack it with a computer, what you need? An algorithm. We don't have a computationally feasible algorithm that can run in the current digital systems, and hence your RSA is secure, because attacker cannot calculate D. Attacker is not able to calculate D because you don't have a algorithm that will calculate you the prime factors of a large. But the point is that this becomes this broken with the help of, so that's where the point. Okay, we will pause now.